might want me to. It's a monolithic product whose whole purpose is to orchestrate continuous deployment pipelines for our customers. So to test how that works, you've got to provide remote systems to test these deployment mechanisms. Broadly speaking, there are two different ways we do deployments. One is using our agent, which runs on, which we test by using ephemeral VMs, or Octopus Deploy can talk directly with SSH to remote systems, which is the subject of our story tonight. So, what we used to do is we had a bunch of what I'm going to call medium-lived virtual machines that lived out on the internet, running SSH and just open to the world. Now, for all you security professionals who I see gently steaming out of your ears, we don't do this anymore. Yes, that's bad. We set a project up to change it quite some time ago. We replaced it with short-lived pods where the test runner would go launch a pod on a remote Kubernetes cluster, run the test, and then tear it down. Kind of looks like this. Now, before I go too much further, who here is like a Kubernetes novice? Like you hear that word and you think like Star Trek alien species? Okay, good, all right. I'll try and explain some things as I go. Any Kubernetes experts? You've broken it in prod? Cool, all right. Learn from our mistakes. On the 25th of August 2022, in the afternoon, our team started getting some alerts in the infrastructure alerting channel. They say this. Now, this is an alert that tells you that a pod is trying to start, but it can't get its image from a container registry. And so it's going to wait for a while to back off the needs. We start an incident, we go in and have a look at our cluster, and then we see this. Now, it's unfortunately smaller than I was hoping for, but it basically is saying that kubelet, which is like a little distributed worker that Kubernetes runs to talk to to manage all the nodes in your cluster, can't speak to containerd, which is the thing that manages containers on those nodes. They're supposed to be right next to each other. This should not happen. We dig a little further and we see that these nodes are really overloaded. That graph might be a little hard to see. The peak at the top there is saying that there are 750 pods waiting to get created. Not created, waiting. This is not good. Normally, down there, let's see if I can get the laser to work. Down here, it's like 5. Historically, there's like 5 waiting. This is over 100 times the normal queue length. We look in and we see weird things going on, like a whole bunch of pods failing, and then some part of the test runner and deployments controllers going and recreating the same pods on another node, killing that node, and it's just infecting the whole cluster, and this is real bad. So we go in, we manually expand out the number of nodes. We also make a change to lower the maximum number of pods from 250 to 125. 250 looks like a big number. I promise you there's a good reason why it was that high. We also ship a change in our test runner to increase the amount of time it waits before giving up. Some hours later, we finally see that little waiting line come down to 0 or near 0. Things are very calm and very happy. About a week later, we run a retro on the team. We look at what contributed to this going wrong. We had small VMs. And on these small VMs, we were running, come on, build work for me, there we go. These VMs were running normal disks, spinning metal, not SSDs. We were setting image pool policy to always, which means every time you start a new pod, even if it's one that already exists, whose container already exists, it's going to go try and reach out to the registry. This increases the load. We were also seeing, because of this weird increase in traffic, 200 of these arriving at a time. You combine all of that, things go boom. We think maybe this was happening because we were getting slightly more bills per minute into our system than usual, but hard to say. And as I mentioned before, this issue where that's fine for one node, but then retries cause it to cascade out through the whole cluster and take everything down. Now, we've just done a retro, we found some contributing factors. As you all know, you do analysis, you fix some things, and this means this will never happen again. Right? 29th November 2023, 15 months later, we get some alerts saying the tests are timing out because pods are not launching. We start an incident, we go in and have a look, we see this. This is a bit different. This is saying that nodes aren't under pressure. And they're under pressure in particular because, there it is, they're under pressure, they're running out of memory, they're trying to kick out workloads that are using more than they should. We see request of 0, oh dear. We haven't requested any resources for these workloads. If you look back at this here, normally you would see a little request there that says, hey, I need some memory, please. We were asking for no memory. So the cluster is just happily jamming more and more and more and more working with these nodes. We ship a change to request some memory. That goes through the system, things eventually calm down. We do another retro. We go, okay, well, we did change the pod limit. We had also in the time in between changed the disks, so that it was a little bit more performant, but we hadn't changed the pod spec. You might think, well, didn't you learn anything the first time? Based on what we concluded the first time, we had made changes. We made changes to pipeline safety. We could deploy it more quickly without worrying about taking things down. They helped us respond quickly, but they didn't prevent the second time. It turns out our system's complex enough that it made it impossible for us to know at what point it was going to fail. We had an over-provisioning system that was supposed to go and create more nodes as we approached limits. Didn't help. We had a janitor system that was supposed to go look for pods that were sticking around for too long. Turns out, when your test runner just decides to stop deleting pods, which is what this chunky graph is here, is an entire test run's worth of pods just hanging around, it couldn't keep up. Now, you might be tempted to call this the root cause of the second incident. And if so, we need to have a talk. I didn't bring the book tonight, but there's a wonderful piece of children's literature called Who Sank the Boat? The story is very simple. 4 big animals get into a boat, it almost sinks, and a mouse jumps into the boat and it sinks. And it finishes with the line, you do know who sank the boat, don't you? Do we know? Looking at just the thing that knocked the first domino over is a bit too simplistic. It limits how you see your systems and what you can learn from their failures. And just because we didn't prevent the second incident doesn't mean we didn't learn things the first time. Come on. For example, we learn we have a complex system, and one where we are facing slowly growing demand all the time. We have to provide something that's predictably reliable against that is really hard. In particular, what are called latent failure modes can't be predicted until you are beyond them. So, I just spent a whole bunch of time telling you how not to do things. And I think that our team made a bunch of reasonable decisions along the way. Thinking about that 250 pod thing, like we originally load tested that. That worked fine when we stood the system up over 2 years ago. But the workload it was using you went from 5 megs of memory to 50 megs of memory. When you've got 200 of those, that's too much. I wanted to make the point tonight that even with great intentions, you might find yourself looking back during an incident and judging your decisions or other people's decisions. In those moments, try to be blameless. Someone called Matt Davis writes a fantastic blog about this, and says that blame is a normal human emotion. That's fine, but it's not going to help you learn things. Try to be empty of blame. So, in summary, what did we learn tonight? Well, other than going easy on yourself, I'd say, look, if you want to remember one thing, even the smallest Kubernetes deployment needs a resource request. I want to thank my colleagues, past and present. I want to thank the people who gave me feedback, and my wonderful partner Cleo, who's home tonight with 3 kids, so I can figure give this talk. If you want to learn more about this, all of that color scheme is horrible on this slide. There's a website called how.complexsystems.fail. It is a very short paper by Richard Cook. It's an easy read, I promise. It's wonderful. Other than that, if anyone's got any questions.
So there's currently no questions in the slide deck, so I'm going to ask a question of my own and then hope some will pop up. Is there a particular process you follow in these like post-incident retros to kind of get to the, I don't want to say the root cause, but the thing that they think?
Yeah, contributing factors analysis, yes. So one of the ways we avoid getting people, or the one team anyway, avoids getting people locked into like working from the trigger backwards is we go, okay, forgetting how things happen, the specific thing that initiated the event. Just start naming things that contributed to this event occurring. We use cloud compute. We use Kubernetes. You kind of start, you try to go what we might call breadth first, you know, and get people to think about, you know, we're a team that's under time pressure. There was a reorg last year, you know, you really go and you kind of bring out all these things to inform your behavior system notes.
Awesome. We have a similar process at my employer, but it's we just ask the question why a lot. Like
yeah. The trouble with 5 whys is that it can lead you in depth first. You can go, we failed to delete pods. Why? An unknown bug in the test runner. Why was there a bug there? There's no tests for the test runner. And you sort of go down that road and you don't look left and right. 5 whys is good, but you need to do more than that.
Yes. Yes, awesome, thank you. Okay, I've got a question here. Failing to define a memory request sounds like it could have been detected by a linter. Did your incident have similar vibes to the recent CrowdStrike outage?
There's two questions there. It could have been detected by a linter if we had one, but we didn't, because we didn't think we needed one, because we hadn't had a problem that could have been detected by a linter. Hindsight is a great thing. I don't blame myself or my teammates for not having made that choice. There's always ways you can improve the system. We still don't have a linter, by the way, but different type of CrowdStrike though. Are there similarities? I think that the scope of impact was different. Like the system we're talking about here doesn't affect the entire world. It affects the engineers who work at my company. And so we take we make risk-based decisions about how we make changes based on that. You know? And so we're maybe a little bit more gung-ho. Well, CrowdStrike's pretty gung-ho, but yeah.
I've got one more here. How is it that it was working fine for a while, even if the memory was not set?
Because there was a constraint we weren't aware of until we became aware of it by things failing. So I rushed over at the time, but the underlying work, we went back and looked, and the underlying workload, the SSHD, and there's actually a Docker daemon in there as well, just went from consuming 5 to 10 megs to 50, 150 megs because of dependency updates and people writing different software and all these various things over the course of like a year and a half. And you can get away with having no memory request if your node happens to be big enough for the number of pods that are normally there. But if it's not, because now the pods use more memory, you get these problems.
Awesome. Well, that's all my questions. Thank you very much.